Okay, let's dive into this. The universe owes nothing because it borrowed nothing. All energy comes from the future and returns to it. Time is the payment plan, heat is the receipt. Just let that sink in for a second. We usually think of energy and time as these big, abstract, totally independent forces shaping reality, right? But what if they're actually part of a strict cosmic financial ledger? What if literally every single action, from a tiny particle moving to a human cell dividing, is a transaction governed by a universal debt? And here's the thing, this isn't just some fun philosophical thought experiment. We're talking about a literal, mathematical constraint that binds absolutely everything in our reality, from the smallest atoms all the way down to the algorithms running on your laptop.
Welcome to this explainer. Today we're going on a profoundly in-depth journey through a concept known as the universal cost algebra. We're going to be looking at a grand unifying framework that is actually written and mathematically verified in Lean 4. Now, if you're not familiar, Lean 4 is this incredibly cutting-edge programming language used by top-tier mathematicians to absolutely rigorously verify complex proofs with zero risk of human error. It is the gold standard. And using this highly rigorous environment, this framework links quantum physics, biology, data compression, and pure mathematics under one inescapable set of accounting rules. By the time we wrap up today, you'll see exactly how the universe balances its books across literally every discipline imaginable.
To really grasp this grand unification, we're going to trace this financial ledger across 6 distinct areas: the universal cost algebra, physics in the vacuum, the price of information, evolution oscillation, transcendent shadows, and finally, the zero-energy universe. Starting off with Section 1, the universal cost algebra.
So the source code defines this fascinating concept called the clinamen. Basically, this is the inescapable baseline cost or the bias of the universe itself. Think of it as a fundamental +1 overhead that's absolutely required to prevent any system from just crashing into absolute zero. It's exactly like having a checking account at a bank. Even if your balance is zero and you aren't making a single transaction, the bank is still going to charge you a tiny monthly maintenance fee just to keep the account open, right? Well, the universe does the exact same thing. You can't get something for nothing, obviously, but more importantly, you can't even have nothing for free. The clinamen is the fundamental maintenance fee of existence. Whether you're trying to store a single bit of data, preserve a biological species, or even represent empty space itself, there's this mandatory baseline tax you literally have to pay just to participate in reality.
And notice how these cost theory files are categorized. These aren't just abstract ideas. These theorems are computationally verified, taking physics and transforming it into a rigorous cost algebra. In this categorical structure, resources are strictly obsessively tracked. When we say categorical structure here, it means every single action requires a defined input, a defined output, and a very precise accounting of the overhead cost. Energy and information are strictly conserved. They cannot be magically duplicated out of thin air. You literally can't just copy-paste reality. Every single interaction is mathematically bound to a budget.
Which leads us perfectly into Section 2, physics, energy, and the vacuum.
And this brilliantly illustrates the cost algebra no-cloning theorem, which mathematically formalizes this exact constraint in Lean 4 code. So, in pure mathematics, there's this thing called a diagonal map. It's an operation that takes an input and perfectly duplicates it. Boom, 2 exact copies for the price of 1. But this specific theorem proves that in a category of cost algebras, this duplication operation is universally forbidden. Why? Well, because if your system has any non-trivial score, meaning it has any actual energy, mass, or information, copying it would mean generating free energy. And that totally shatters the universal ledger. The absolute only thing in the universe that can be freely duplicated is the vacuum itself. The vacuum has a mathematical score of exactly 0. And, well, copying 0 costs 0. This profoundly reframes how we even look at physics. Energy conservation isn't just some arbitrary rule imposed from the top down. It's a direct, inevitable consequence of the universe literally not allowing free copy-pasting. And because nothing can be cloned for free, energy has a strict life cycle. It operates exactly like taking out a financial loan. Step 1, when you create a bit of information, you immediately incur an energy debt from the future. Step 2, as time passes, simply maintaining that bit incurs a continuous storage cost. The clock is ticking and the bill is running up. Step 3, when you erase that bit, the borrowed energy doesn't just magically vanish. And this is where Landauer's principle comes in, which proves that information is literally physical. When you erase a bit, those microscopic states of information have to go somewhere. The universe forces you to repay that debt, and it expels it into the environment as actual, physical kinetic energy, which we experience as heat.
So, erasing data physically raises the temperature of the room. This definitively, permanently proves the impossibility of a perpetual motion machine, because every single cycle creates debt, and that debt is always paid in heat.
Let's move to and see how this builds into Section 3, the price of information.
This brings us to a fascinating concept called Solomonoff induction. Basically, this is the deep mathematical formulation of Occam's razor, the principle that simpler explanations are inherently better. Solomonoff induction assigns a probability weight to every possible program that can produce a piece of data. The math is elegant. The formula is 2 to the negative power of the program's length. Let's break that down. If a program is just 10 bits long, its probability weight is 1 over 2 to the 10th power, or 1 in 1024. But if it's a clunky, messy 100-bit program, the probability just plummets astronomically. Shorter, simpler descriptions get exponentially higher weight. But wait, remember the Kleinemann, that mandatory maintenance fee of the universe? A 0-bit program would technically have a weight of 1, implying absolute 100% certainty. But the math entirely forbids this. Absolutely no string has 0 complexity. Even a program that just says output nothing requires at least a 1-bit command just to signal the end of the message. You always have to pay the fee.
Notice how the Occam factor is perfectly balanced on the ledger here. Ideally, we'd want to calculate the absolute shortest possible code to produce a piece of data, a concept known in computer science as Kolmogorov complexity. But there's a huge catch. To find the absolute shortest program, you'd literally have to test run every possible program. And some programs get stuck in infinite loops and just run forever. You can never actually know if they're eventually going to finish or not. This is famously known as the halting problem. And because the halting problem is completely unsolvable, true Kolmogorov complexity is impossible to compute, period. So instead, this framework establishes minimum description length as a computable upper bound. You always pay what's called the Occam factor. Basically, whatever budget you spend describing the data is precisely what you lose in generalization power.
To really see how this budget constraint works in practical, real-world data compression, the sources highlight something called Fibonacci coding. It uses Zeckendorf's theorem, which states that any whole number can be represented as a sum of non-consecutive Fibonacci numbers. Non-consecutive is the magic word here. Because of this rule, the code has what's called a greedy gap. This mathematically guarantees that 2 consecutive 1 bits will never, ever appear naturally in the data flow. And because a natural 1-1 is impossible, you can intentionally use 1-1 as a hard physical wall, a terminator sequence. It makes the code prefix-free and self-delimiting. You don't need some external framing data to tell the computer where a file ends. The file announces its own end. Imagine a catastrophic system crash where data gets corrupted and bleeds into other files. In standard binary, that destroys the whole shebang, but Fibonacci coding is intensely robust. Because of that 1-1 wall, a flipped bit only corrupts a single code word, halting the damage instantly.
So the crucial point is, the cost of this incredible security comes down to a very specific number, 1.44. You see, Fibonacci coding uses more bits than standard binary coding. For example, the number 21 takes just 5 bits in binary, but it actually requires 8 bits in Fibonacci coding. The mathematical overhead ratio comes out to log base 2 of the golden ratio, which lands right around 1.44. And this isn't just some weird quirk of mathematics. That extra 1.44 overhead is the literal insurance premium the universe forces data systems to pay if they want to survive entropy. You are paying a slightly higher storage tax on the universal ledger specifically to buy immunity against catastrophic system crashes.
All right, let's pivot to Section 4, evolution as an oscillation.
So, in biological evolution, there is this fierce fundamental tension between monoculture and diversity. First, you have the Skyrim's model, which heavily favors monoculture. Imagine a massive, genetically identical monocrop farm. It is incredibly efficient right now, exactly at time equals 0, yielding massive output. But it's entirely myopic. If a single, specific disease sweeps through, the entire crop dies overnight. On the other hand, you have the forest model, which represents a wild, untamed rainforest. It is highly inefficient today. It's messy, it's diverse, it's constantly competing with itself for resources. But it is incredibly farsighted and optimal for a large timescale. Why? Because extinction is an irreversible loss. In the universal ledger, the option value of a dead species is permanently, unchangeably 0.
Now, what's really interesting about this slide is how the sliver exploration theorem elegantly resolves this massive biological tension. Neither the purely optimized Skyrim's monoculture nor the purely messy forest diversity actually wins.
The universe absolutely does not pick a static winner here. The code mathematically proves that the true fixed point of survival is an eternal oscillation. It's a biological breathing. Think of it exactly like a pendulum constantly swinging back and forth. The system continuously pays an exploration penalty, literally burning a tiny sliver of energy efficiency just to keep diverse options alive. It willingly pays this tax to keep the pendulum moving rather than letting it rest at a dead stop, because a dead stop means extinction. That constant friction between pure efficiency and chaotic diversity is literally the heartbeat of evolutionary survival.
Moving on to Section 5, Shadows of Transcendental Numbers.
Let's dive into some pure mathematics for a second. The famous Lindemann-Weierstrass theorem proves that numbers like e and pi are transcendental. This means they cannot be the root of any integer polynomial. You can't just plug them into a standard algebra equation and ever hit exactly zero. But proving this normally requires an infinite mathematical search, and here's the catch. The universe's computer does not have infinite RAM. A strict finite ledger simply cannot compute forever. So Lean 4 constructs what's called a shadow. Instead of trying to calculate to infinity, it draws a strict finite computational box. It uses bounded enumeration to prove that inside this specific box, when checking small integer polynomials, the rational approximations of e and pi do not hit zero within a 1/110th tolerance. The framework brilliantly leverages this finite computable shadow to prove the exact same truth without wasting impossible processing power on infinity.
To make this mathematical shadow work, the precision has to be unbelievably calibrated. For the number pi, the theorem requires a calculation depth of exactly 60. At depth 60, pi is pinned down to about 10 to the negative 40th power. To put that completely mind-boggling number into perspective, 10 to the negative 40th power is so infinitesimally small, it's like trying to measure the width of a single atom compared to the entire observable universe. At this exact depth, it is tight enough to cleanly separate pi's true value from any small algebraic relation. Depth 60 is the exact energetic budget the universe spends to keep pi transcendental. Any deeper, it's a waste of universal energy. Any shallower, the math completely falls apart.
And finally, Section 6, the zero-energy universe.
This right here is it, the ultimate master theorem encoded in the entire framework. At the zero time step, the very absolute beginning, the total storage debt of the universe is exactly zero. The magnitude of this concept is just staggering when you really think about it. The Big Bang wasn't the spontaneous magical creation of free energy, it was the taking out of a massive cosmic loan. Every single thing we experience, the immense burning heat of a galaxy, the intricate complexity of a compressed digital file, the diverse breathing of a rainforest ecosystem, the precise 60-depth shadow of a mathematical constant, it is all borrowed Klein. It is a temporary fluctuation from the vacuum, perfectly balanced on a cosmic ledger that must, inevitably, return to absolute zero. Which leaves us with a rather profound realization today. Time is literally the mechanism by which the universe processes its energetic repayment. So if the universe ultimately owes nothing because it originally borrowed nothing, what cosmic debt are you currently paying off with your time? Thank you so much for exploring the universal cost algebra with me. Keep wondering, keep questioning, and I'll see you in the next explainer.